Welcome to Image Formation by Lenses. In this video, we're going to be talking about how light is reflected by an object and then passes through a lens to form an image on the other side. So a brief overview of what we're going to go over in this video is we're going to start with how light is refracted and some properties of light. Then we're going to go over the two types of lenses, convex and concave. We'll cover the power of lenses and then how image formation works. And then we'll go over a specific example of image formation in our eyes. Before we get into how lenses form images, let's back up and talk a little bit about how light works. When light interacts with matter, it's a lot bigger than the light particles themselves. They take on ray-like properties, not wave-like properties. When light rays pass through a medium and that medium affects it, like slowing down its speed or changing its direction, that's called refraction. Different mediums have different effects on light, and that's called the index of refraction. We can show that with this equation, n equals c over v, where n is the index of refraction, and we can calculate how much the angle and speed of light are going to change. N is this index of refraction, c is the speed of light, which is 3 times 10 to the 8th meters per second, and v is the observed speed of light. Once we know the index of refraction, or how much a specific medium will change the speed of light, we can determine the angle a ray will travel in a new medium. So the illustration below shows an example of two cars that kind of helps us think about how this would work. The cars are traveling from asphalt onto sand, and obviously they are going to be able to travel faster on the asphalt than the sand. So the red car is going in a straight line from the asphalt to the sand, and it won't change direction, it will just slow down. The green car, however, is going at an angle from the asphalt to the sand, and once it hits the sand, its right wheels are actually going to hit the sand a little bit before its left wheels. So its right wheels are going to slow down before its left wheels, meaning that the car will slightly change direction. And this concept can be explained by the equation n1 times sine theta of 1 equals n2 sine theta of 2, where n1 is the index of refraction for the first medium and n2 is the index of refraction for the second medium. And sine theta is the angle at which the car is traveling. Now applying that to lenses, let's start with a convex lens. In a convex or convergent lens, all rays that enter perpendicular to the lens will be bent so that they cross at the same set point on the other side. That's called the focal point. The distance from the focal point to the center of the lens, this distance here, is called f. And we can determine the power of the lens using the inverse of the focal length. So that is shown by the equation P equals 1 over f. Moving on to concave or divergent lenses, the same principles of focal length and power apply. And it's easy to remember the difference between convex and concave lenses because, as you can see in a concave lens, they bend slightly inward, forming an almost cave-like shape right next to the lens, as we can see in the image below. Once light passes through a concave lens, it is bent away from all other light rays. So all light rays diverge in a concave or divergent lens, hence the name divergent lens. We find the focal point on the same side of the object that the light is coming from. So if our object is somewhere over here and all the light rays are coming perpendicular to our lens, we find our focal point by tracing the new angle on the other side of the lens all the way back to where they all converge on the same side of the lens as the object. And that is our focal point for a concave or divergent lens. Right back, if I can get my mouse to work, right here. Now that we understand how light rays are refracted and the difference between convex and concave lenses, let's talk about how image formation actually works. In doing that, we need to make an assumption called the thin lens assumption, because as we look at this lens, it's obviously thicker in the middle and thinner at the top and the bottom, which means that a light ray would travel through at the top and bottom faster and take longer in the middle. But we're going to assume that our lens is thin enough that the time difference is negligible, and we are also going to assume that light only bends once instead of once as it enters the lens and once as it leaves. Okay, looking at this image, we can see a red arrow on the left, and that's our object. Light is being reflected from our object in all directions, but we're going to focus on the light rays coming from the top of the object, and we're going to use 3 different rays that are going to help us understand image formation, even though there are many light rays coming from this point. Starting with our red line, line number 1, this line is perpendicular to our lens, which means that after it passes through our lens, it's going to pass through the focal point as well. Our second ray of light, the green line, number 2, is going in a straight line through the center of the lens. And just like our car earlier in this video that went straight from pavement to sand, it's not going to change direction. It's going to continue in a straight line through that lens. And then our third line that we're going to use, number 3, shown in purple, is going to pass through the focal point on the same side as the object, which means that after it passes through the lens, it is going to continue perpendicular to our lens. Now, as you can see, these 3 lines converge on the other side of the lens on a single point right here. And this point is where an image will be formed, where all of the light rays reconverge. Now, we could do the same thing for any point on our object. For example, if we were to take 3 rays of light from this point right here on our object, they would reconverge right here on our image. And if we were to do the same thing for this point in our object, those rays of light would reconverge right here on our image. And that is how our eyes are able to perceive images. That is how images are formed. Now that we've gone over some of the concepts behind image formation, let's go over some of the specific values and mathematical equations for image formation. And to do that, we're going to need to go over some terminology. Starting with F, we've already gone over F, which is the focal length. I just wanted to note that F is positive for converging lenses and negative for diverging lenses. Next, let's go over M, which is magnification, which just tells us how much bigger or smaller our image is than our object. So if our object is smaller than our image, that means that our image has been magnified and M will be greater than 1. If our image is smaller than our actual object, it means that our image has been demagnified and M will be less than 1. And another note, M is positive for an upright image and negative for an inverted image. So looking at our picture below, we can see that our image has been inverted, meaning that M is going to be negative. We can also see that our object is larger than our image, meaning that M will be less than 1. Next, DI is the distance of the image from the lens, this length from here to here. DO is the distance of the object from the lens, this length from here to here. HI is the height of our image, or this distance from here to here, while HO is the height of our object, the length of from here to here. And we can use those terms to help us, if we know some of those values, we can use them to solve for other values, as shown in the equations on this slide. Starting with 1 over DI plus 1 over DO equals 1 over F. meaning that if we knew the distance of the object from the lens and we knew the focal length, we could solve for the distance of the image from the lens, or vice versa. Right below that, we see that m is equal to negative di over do, or m is equal to hi over ho, meaning that if we know the height of the object and the height of the image, we can solve for the magnification. Same thing goes for the distance of the object and the distance of the image. And finally, I have two more terms I'd like to go over. Real images are images where light rays actually converge at a point, which we can see in our picture below to be right here. Our light rays actually converge there. In a virtual image, light rays only appear to converge at a certain point because of the way that a lens bends light. So to review these terms, using our picture below, m is going to be a negative number because our image is inverted, and it is going to be less than 1 because our image is smaller than our object. We know f to be the length of our focal point to our lens, our distance of di to be our distance from our image to our lens, and do to be our distance from our lens to our object. We know that hi is the height of our image and ho is the height of our object. Now that we know how image formation works, let's look at how it works in our eye. In this picture, we can see a tree on our left, which passes through the lens of our eye and comes into focus, reconverges at the back of our eye. So the rays of light that start at the top of the tree diverge and then reconverge at this point in the back of our eye, where the rays of light coming from the bottom of the tree diverge and then reconverge at the back of our eye right here. This means that all of the images that our eyes see are actually inverted, and our brain has just taught itself to turn them around so they all seem upright to us. And this part of our eye where images are formed is called the macula, and specifically the center of the macula is called the fovea, and this is how we are able to perceive images. I hope that this video has been helpful in helping you understand how light is refracted and how convex and concave lenses work and how image formation happens. Thanks for watching.